So this is part 2 of our notes for atomic structure. As a recap of part 1, I want to summarize Coulomb's law. Distance and magnitude ends up being the two factors that end up attributing to the forces of attraction between the subatomic particles of protons and electrons. As the distance changes, the further away that those particles get from each other, the force drops off by the inverse square. Magnitude is a direct relationship. Higher the magnitude of the charge, the higher the attraction is going to be. Photoelectron spectroscopy, or PES, was used to determine the energy levels and sublevels. The energy levels are separated by a power of 10. So when you look at a photoelectron spectroscopy graph, you would see that the difference in the sections that are a power of 10 different from each other would be an entire different energy level. And then within that, you would see 2 separate spikes, or maybe 3 separate spikes within that range, and those would be the sublevels within that. And those sublevels have acronyms of S, P, D, and F. And we mostly have talked about the sharp peak and the principal peaks so far. Due to Coulomb's law, electrons will get as close to the nucleus as they can. If there's something else in the way or repelling them away, of course, they can't do that. So here is a photoelectron spectroscopy graph of calcium. Take a moment. How many energy levels are there? With this graph, there are 4 energy levels. We have this one being the first energy level, having the highest energy. These 2 peaks is the second energy level. These 2 peaks make the third energy level, and this makes the 4th energy level. You'll notice that I have 2 sublevels in energy level 2, and energy level 3, I have 2 sublevels as well. Can you write out the electron configuration for calcium based off of this data? In other words, if I didn't tell you it was calcium, would you be able to figure it out? Take a moment. So for the electron configuration, this would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So let's continue our discussion. So why are there only 2 electrons on the first energy level? Well, and I know this sounds like a tangent, but it's truly not. Let's talk about dinner plates. If you were to calculate the area of a 10-inch diameter dinner plate and a 12-inch diameter dinner plate, what percent increase would you get for that 20% increase in radius? Because if we go from a 10-inch plate to a 12-inch plate, that's a 20% increase in radius. What happens, though, to the area because of that? Take a moment to calculate the area of each, and if you can as well, determine the percent increase for the area. So if you have a 10-inch plate, you have 78.5 square inches of surface area. If you have a 12-inch plate, it's going to be 113.1 inches squared inches of area. So for the 20% increase in radius, you get a 44% increase in area, not volume, my mistake. So you'll notice that in the 1960s, if you had an 8-inch to 9-inch dinner plate, that holds only about 600 calories. But now in the modern era, our 12-inch dinner plates, which would have been a platter back then, can hold up to 1,900 calories. So that said, how does this all end up relating to atomic structure? Well, atomic structure is based off of volume rather than area. A small increase in radius will make a huge difference in volume, because you'll notice for example, if we were using a sphere, 4/3 pi r cubed ends up being the relationship that we're looking at with volume, where the area was only squared. Now we're talking about a cubed difference. So if we're looking at the energy levels, you'll notice that the first, second, third, and fourth energy levels don't all hold the same number of electrons. It's constantly increasing. First energy level holds 2, second holds 8, third energy level can hold 18, fourth energy level can hold 32 electrons. Why would that be? Another thing to note before we go on and answer the question about why we can hold more electrons, do you notice that here's the nucleus, and that the difference from the first energy level to the second energy level is further distance than it is between the first energy level and the second, between the second energy level and the third? And you'll notice that the difference in these radii is getting shorter and shorter. So the least gap is between 7 and 6. The next larger gap, which is not much larger, is between 6 and 5, and it gets a little bit bigger each time we get closer into the nucleus. Something we'll talk about later, but I wanted to point that out now too. So why only 2 electrons in the first energy level and 32 for the fourth energy level? Small increases in radius make huge increases in volume, because once again, of that cubed value. So where does this all stem from? Why is that so important? Well, here's a set of atomic emission spectrum. So these atomic emission spectrums mean that if you have hydrogen and you were to excite it, it's going to release some light. That light is going to not necessarily be a full rainbow, but a very distinct set of lines. And you'll notice that each element seems to have its own set of lines. Mercury has a different set of lines than neon, as in helium or sodium or any other element on the entire periodic table. So why is that? Where did those lines come from? And all of this information that we've been building on will actually help explain where this comes from. So what happens is that if you have an electron in, let's say, the first energy level, and you excite it into the seventh energy level, and it falls back down to the first energy level, it's going to emit light from it. So for example, if we have helium, or not helium, hydrogen, and we were to excite that electron in the first energy level, and it goes to the second or third or fourth or fifth or sixth, each time it falls back down, it's going to emit a different wavelength of light. So that comes into the equations on light. So what are the light equations? Well, there are 2 that we're going to be dealing with. That's what's also on the College Board equation sheet. That energy is equal to Planck's constant times frequency, or E is equal to h nu. The other equation is C is equal to lambda times nu, where C is the speed of light, lambda is the wavelength, and nu is the frequency. The constants that are in there are speed of light and Planck's constant. Planck's constant is h. It ultimately ends up being the smallest packet of energy for a particular photon. So a photon, by the way, is a particle of light. And Planck's constant ends up being 6.626 times 10 to the negative 34th joules times seconds. Not divided by, but times seconds, divided by either a photon or a wave. And we will talk about the difference between the wave-particle duality a little bit. That's going to be h, or Planck's constant. Speed of light is going to be c, which is 2.998 times 10 to the 8th meters per second. These end up being constants. So here's a couple of sample problems for you to try. What is the frequency for 480 nanometer wavelength? 1 nanometer, by the way, is 1 times 10 to the negative 9th meters. Take a moment. Here's the ultimate solution. You'll notice that I have a tendency to solve my problems first by doing a symbolic solution. You'll notice that I end up taking the equation that I needed of C is equal to lambda times nu, and I divided both sides by lambda. So I got C divided by lambda is equal to nu, or frequency. And then I plugged in each one of them, and you'll notice that I have 6.25 times 10 to the 14th waves per second. Now, a per second, by the way, is also called a hertz, which is abbreviated as Hz. For problem number 2, we're actually going to use the answer from the previous problem. And now what we're doing is going to figure out how much energy is in a photon with a frequency of 6.25 times 10 to the 14th hertz. Solution for that, once again, I end up symbolically solving it first. In this particular case, I did not have to rearrange the equation to make it happen. I was just able to use the equation directly off of the equation sheet. So E is going to be equal to 6.626 times 10 to the negative 34th joules times second per photon. And then I have 6.626 times, I'm sorry, 6.25 times 10 to the 14th photons per second, which is that hertz that we're talking about. You'll now notice that the photons and photons will cancel, and I end up with 4.14 times 10 to the negative 19th joules. So that ends up being more or less the quanta for that particular photon, or the smallest packet of energy that is necessary for that particular particle of light. So how much energy is in 1 mole of those photons with a frequency of 6.25 times 10 to the 14th hertz? All you had to do with that particular problem was multiply your answer from the other problem that we solved by Avogadro's number, or 6.022 times 10 to the 23rd. And for ease purposes, I converted mine to kilojoules per mole, so that way the number was not going to be 24,900, but rather 249. So back to that entire idea of particle or wave or both. I know that the textbook and many other people end up talking about Schrodinger's cat. Is the cat both alive or dead? How can it be both? You know, and there's that entire discussion. And if you're more than welcome to look those things up, there's all sorts of stuff online about that. What I'm going to do instead is, of course, take a slight tangent and talk about burning steel wool. If you just take a look at this particular picture, you can see very distinctly that that's steel wool, and you can see the sparks that are burning on the inside of it. But imagine now that if I were to take that chunk of steel wool and start spinning it really quickly around in on a string. And as a matter of fact, that's what these photographers ended up doing. They ended up taking a wire whisk, stuffing it full of steel wool, igniting it at nighttime, and then they did time-lapse photography on it. And they specifically did time-lapse photography on it so they can get this effect of where you see this entire ring going around, or in this particular case, almost like a sphere that's going around the particular person who's twirling the wire or the string. Now, if I were to take an individual picture of this, what I would end up with, instead of this time-lapse photography where you get that line going, you would get something a little bit different, right? You would get pretty much just a spot. Like if it were right here, you'd get a spot of where it happened to be, and you would get the line or the string that's attached to it, and you wouldn't get this cool form that's going around in the particular circle, but you get a dot. Well, the dot would be a particle, and the fact that we're looking at the shape that is created through its movement, that shape that is created in its movement is what we're going to call the wave. So how can something be a particle and a wave at the same time? Well, it depends on how you look at it. In this particular case, we're looking at the wave form that's being created by the man spinning the steel wool around in a circle or a sphere. But if I took a very short glimpse at it, what I would end up with would be a particle instead. So that's probably the easiest definition that I could give. That is not exactly correct, but is going to do well enough for what we are going to be working with. All right, so this is time-lapse. What would a quick picture of this look like? As we talked about, there'd be one spot rather than the entire circle that would be in effect. Does it have to be a sphere or a circle? Well, no, most definitely not. It depends on how you decide to start spinning the thing around. You'll notice in this particular form, they did a series of a figure 8. So why can the s orbital hold only 2 electrons while the p orbitals can hold 6? Well, just like we said before, if there's more distance from the nucleus, we get more volume. But how can we fill the rest of that space? Well, we're going to have different shapes involved. When it comes to s orbitals end up being spherical in their shape. And this ends up being an s orbital that's cut in half so you can see the interior. The College Board will most likely not talk too much about the nodes that are in between these, which nodes would end up being empty space. So for example, if this is the 1s orbital, you'll notice that it's just basically one node, and in here we've got a node or a series of an empty space in between this layer and that layer, and that would be the waveform that would be created by the second s orbital. The third s orbital, you'll notice, is a larger diameter than the other two, and it has more nodes or empty spaces in between. I wanted to point out the nodes because I know that the textbook did a okay job of explaining it, but I thought seeing the pictures with my explanations might be more useful. P orbitals will also have the potential for nodes, but I'm not going to show those here. But the P orbitals end up being more in a dumbbell shape. And you'll notice that there are 3 sets of dumbbells, one along the x-axis, one along the y, and one along the z-axis. I want to make sure that you recognize that each one of those represents one orbital. An orbital is something that can hold 2 electrons. So if I were to combine all 3 of those orbitals together, I would get this structure with the center portion of it down here being in the very middle of this being the nucleus, and then each of these overlapping each other. These groups can hold a total of 6 electrons. Each one of these sets would be able to hold 2 electrons. So here's a diagram of the overlapping of a 1s orbital, a 2s orbital, 2 p orbitals, and a 3s orbital all around the center of the nucleus itself. I'm going to leave this here for a moment so you can actually take a look at it and try and see if you can absorb the whole thing. I will talk through it a little bit too. So nucleus, of course, being in the center, you'll notice that the 1s orbital ends up being this small sphere in the center. And then the 2s orbital is the next sphere. The 3s orbital is that largest sphere. You'll notice the 2p orbitals end up sticking out of the sides, filling in some empty spaces that were not being filled by other orbitals before. Here are the d orbitals. You don't have to worry about memorizing any of these shapes per se, but I do want to make sure you recognize that even though that this d orbital has 4 lobes in it, this orbital can still only hold 2 electrons. This orbital can hold 2 electrons. This funky thing with the donut can only hold 2 electrons. Each one of these would hold 2 electrons apiece, giving all 5 of those together the ability to hold 10 electrons. The f orbitals get even more funky. Again, you don't have to worry about the shapes, but bear in mind each one of those, again, of those 7, can hold exactly 2 electrons in each one of those structures. Here ends up being a gallery of the entire set of orbitals that are, at this point, theorized and mathematically solved for, and we have some good evidence to show that they probably behave this way. You'll notice that the 1s orbital, no nodes, 1 empty space in between, 2 empty spaces, 3, 4, and 5, and so forth for the s orbitals. You notice all the p orbitals end up having a dumbbell type shape, but you'll also notice that it has nodes as well. Same thing with the Ds as you're going through, and then the F block at the bottom. Again, don't worry too much about knowing the shapes. I figured that just having a visual might be helpful for some. The ones that you should probably have in your brain for the AP exam would be the S orbitals, knowing that it's a spherical in shape, and the P orbitals, which end up being more dumbbell in shape. All right, so at this point, which would be easier? A complicated wave pattern that is closer to the nucleus, like the 3D orbital, or a simpler wave pattern that's slightly further away from the nucleus, like the 4s? So in other words, which one do we actually going to fill with electrons first? The 4s, which is a nice simple sphere to try and fill, but it's a little bit further away? Or are we going to go in that complicated D pattern and be slightly closer to the nucleus because it's a 3rd energy level instead? Now there is a means that you're actually going to fill the 4s first and then the 3d. There is a sequence, and here is a sequence of the orbitals that the electrons are going to fill up in. And I'm not going to recommend that you actually memorize this because we're going to be able to use the periodic table to help us figure it out. But I do want to show you how the energy pattern works. You'll notice we're always going to fill in the 1s orbital first, and then the 2nd energy level, or the 2s and the 2p. But you'll notice once we start filling the 3rd energy level, the 4s actually ends up getting filled in before the 3d, then the 4p, the 5s, etc. So you'll notice that it ends up being kind of mixed up and confused. Well, how does that work when it comes to the periodic table itself? Well, when it comes to the periodic table, you just really need to read the periodic table as if it were a book from the top left corner from left to right. 1s. So you'll notice these two columns here end up being the s block of electrons. This section over here from 3a to 8a ends up being the p block, other than helium, which ends up being in the s block. You'll notice that this section in the middle is the D block of elements, and the bottom two rows that are not quite attached but actually fit in right in this area are going to be the F block of electrons. So if we're going through this and I'm going across from one to another, this would be 1s, 2, 2s, 1, 2s, 2, 2p1, 2p2, 2p3, 2p4, 2p5, 2p6, and then the 3s, the 3p, the 4s, but then you'll notice that I come back down. Once I hit this fourth row and I hit the transition elements, the transition metals, I specifically go back to the 3d, then 4p, 5s, and so forth. So you basically just read this like a book. Now, I would recommend that you actually take a moment and copy that into your notes, or at least a rough sketch of it, so you have a good format in your brain of how it's going to work when you can look at the periodic table. So if we would take a look at the periodic table once again and start doing the relationship overall to the orbital structure, you'll notice that I wrote out that entire section once again. This time I didn't color code it, but I did block it up into chunks based off of the row that it's on the periodic table itself. First row on the periodic table is just the 1s, helium and hydrogen. The 2s and the 2p can hold 8 electrons, and that's where you're going to get that entire second row going from lithium all the way to neon. Third row ends up being the 3s and the 3p. Fourth row ends up including the 3d, because now we hit those transition metals. Same thing with the fifth row. We have the 4d. You'll notice that it's always one energy level less than the row you are in for the d block. Once we hit the sixth row, that's when we're going to hit the f block of elements. And you'll notice that it goes down to the 4f. And the seventh row ends up being 5f. So this sequence follows exactly with this periodic table. For example, if we're looking at row 6, you'd start off with row 6, 6s2, then you would do 4f14, then we're taking a look at 5d10, and then 6p6. So at this point in time, let's go ahead and get some practice. I'd like you to, for a full electron configuration, which means you just write out everything, go ahead and write out the full electron configuration for bismuth. I'll move back to the periodic table so you can actually use it. And to let you know, bismuth is right here. You should have come up with 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, 5d10, and 6p3. From this point, what I really want to point out to you is that everything except for this last row, so this is what the last row was, and this was everything on the inside of that. We're going to call everything on the inside portion of that core electrons, and those core electrons end up being shielded. They end up being shielded from they are shielding the nucleus from the valence electrons. So these valence electrons are the ones that are on the outside edge. The valence electrons are really going to be the ones that we're actually more concerned about than anything else, because those are the ones that are actually going to chemically react. They're the ones on the outside energy level. So what's an abbreviated electron configuration? So instead of having to write the entire thing out like we just did a moment ago, we're going to do abbreviated electron configurations more frequently. What do? Well, you write out only electrons that for the row that it's in, and you use the noble gases as the core electrons. So you'll notice that I've got this entire section right here is the full electron configuration for bismuth. But if I wanted to summarize this down and use the abbreviated electron configuration for it, what I could do is all of this to here all represents xenon. So what do I write down? Abbreviated electron configuration becomes Xe, 6s2, 4f14, 5d10, 6p3. Okay, so that should make life a little bit easier so you don't have to write out the full electron configuration all the time. Let's go ahead and have you get some practice on this. Write out the abbreviated electron configuration for those 6 elements. Here are all the answers for those. You'll notice that I ended up doing the abbreviated electron configuration for it, and granted with nitrogen and oxygen, the only difference that helium ends up being is actually just a 1s2, so it probably was just about as much work to write out He in brackets as it would have been to write out 1s2. But it does differentiate the fact that the 2s2, 2p3 ends up being the valence electrons that we're more concerned about when it comes to nitrogen. The rest of those electron configurations are written out. Take a moment to compare your answers. All right, so let's take a look at these a little bit more detail. How would these turn into ions? If you've got chlorine, you've got strontium, how are those things actually going to turn into an ion? Taking a look at chlorine first, chlorine ends up becoming the chloride ion. And you'll notice that I'm now starting to write out this. Well, here's the abbreviated electron configuration. Now I'm starting to write out what's also called an orbital diagram. You'll notice that the orbital diagram ends up representing the individual orbitals within the sublevels. So let's talk about that. The 3 represents the energy level that we're in. The S is the sublevel, because remember there was a division in between the S's and the P's. There were more P electrons than there were S electrons. And the S electrons end up having a higher energy, so they're going to be at a lower state or closer to the nucleus. So that's why I drew them, or why they got drawn a little bit lower down. As far as that, how many electrons can fit in there? Well, 2 electrons, one spinning upward, one spinning downward. As far as the direction of the arrows, there are other notations that that textbooks use. I'm going to be using arrows because that seems to be the most common that I have seen. Then you'll notice when it comes to the chlorine, we've got 5 electrons in the P. So we got 1, 2, 3 going up, 4 and 5 coming down. Then the chloride ion ends up being the fact that we end up adding an extra electron. When we add that extra electron to become the chloride ion, you'll notice that I have completely filled the outside energy level, and now I have pretty much a noble gas configuration, which is going to be like argon. And we've talked about this before, that when atoms become ions, they more or less get the configuration, the same electron configuration as a noble gas. So what's the chloride ion charge going to be? Well, it still only has the number of protons it started with, but now it has an extra electron. So the charge on the chloride is going to be a -1. Strontium, on the other hand, was the Kr 5s2. You got the electrons going up and down. And when strontium becomes an ion, it ends up losing 2 electrons, which more or less it becomes, again, a noble gas. But this time the orbital diagram just means I take out these 2 arrows. All right, so this diagram has a whole lot to absorb to it. You don't have to worry about copying it down, but at this point what we're really doing is talking about some of the conceptual ideas that you might be asked in essay questions on the College Board exam, or for that matter on my test. Let's compare lithium ion to lithium, the lithium as an atom. You'll notice that the lithium ion ends up being smaller than the lithium atom. So you notice this side is the lithium atom, this side is the lithium ion. Why would that be? If you ended up saying that because lithium lost an electron and also lost that entire outside energy level, and it'll end up getting smaller in size, that would be a perfect answer. So let's go ahead and take a look at oxygen next. So oxygen to oxygen 2-. So if I'm looking at this one right here, you'll notice that oxygen as an atom this time is now on the left, and oxygen as an ion is on the right. It went from an oxygen atom to an oxygen with a 2- charge. What happened to the size? Why did the size go up? By adding 2 extra electrons to oxygen, the protons are still trying to hold on to all those additional electrons, and because those additional electrons are there, those extra electrons are now repelling each other slightly and pushing them further out. So you'll notice that I have an increase from 73 picometers up to 126 picometers by adding those 2 extra electrons. Now let's compare the size of O2 minus to F minus. You'll notice that O2 minus ends up being 126 and that F minus is 119. Why did it go down? I only added 1 electron here. Why did it go down from 126 down here? Well, remember, this one, aside from just only gaining 1 extra electron, also has an extra proton that oxygen didn't have. All right, other question. Why are the sizes just getting bigger as we're going down the periodic table every time? When we're going down the periodic table, we end up adding energy levels. And each time we add an energy level, it's going to get further away from the nucleus. So take a moment, rank the following by increasing size and explain why it is increasing in size. You'll notice that I ended up putting down N3 minus. I'm sorry, not increasing in size, decreasing in size. I got N3 minus, O2 minus, F minus, and AR. And you'll notice what I wrote down is you'll notice that all of them have 10 electrons because nitrogen as an atom starts off with 7, but gaining 3 extra electrons to become the -3 charge means it now has 10 electrons. Argon naturally has 10 electrons. Fluorine with a -1 charge has 10 electrons. Oxygen with 2 extra electrons has 10 electrons. But you'll notice that the number of protons ends up constantly going up with the way that I sequence them. So in this particular case, it's not the distance from the nucleus that we're so concerned about, but the magnitude of the positive charge of the protons, going back to that idea of Coulomb's law. Now, there's a term that I've seen the College Board use from time to time, including textbooks use from time to time, and called the term isoelectronic. Isoelectronic means that they have the same electron configuration or the same number of electrons. So these are just the atoms of the periodic table. So these are not ions. Can you use your knowledge of atomic structure at this point and electron structure to explain the changes as we go down the periodic table? Let's do that first. Why, as we're going down the periodic table, are the atoms getting larger? And why is it as we're going across the periodic table that the atoms are getting smaller? As we're going down the columns, you'll notice that we have a new energy level, which means it's further away from the nucleus. Again, going back to Coulomb's law. Further away from the nucleus, this means that the force is going to be much smaller. Going across, it's still the same energy level. However, we're going to have more protons in it. Because we have more protons, those electrons are going to be pulled in toward the nucleus tighter. All right, so the other day we looked at some photoelectron spectroscopy data between nitrogen and oxygen. And I wanted you to notice something. Now, I remember the other day we ended up talking about the oxygen ends up having its peaks shifted in general toward the left or higher energy. But that's not 100% true. Look at the 2p peak. So I'm looking at nitrogen here at 1.4, and you'll notice that when I go to oxygen, it actually, instead of shifting to a higher energy, it actually shifted to a lower energy down to 1.31. Why might that be? Well, let's take a look at the electron configuration. Nitrogen, we've got, just like you had written before, 2s2, 2p3, and its orbital diagram would end up being exactly this. You'll notice that we have 1 electron in each one of those orbitals. But in oxygen, I've got 4 electrons in the p orbitals, where I have 1 in each of the p's, and then we start to double them up, where you get a second one in here. So what is that actually going to cause? Well, you notice with the nitrogen, I've got my peak again for the 2s, ends up being at 2.45, but with the oxygen, it's 3.04, which means the addition of that extra proton ended up pulling that energy to a higher energy for those electrons. But for the p orbitals, you'll notice that for the p orbital electrons, it's at 1.4, and this is now at 1.31. The explanation that's given for that is because the addition of this extra electron in the p orbital that is now paired up is causing an additional repulsion, which is now causing all of those electrons to be able to be released at a lower energy. So what about ions in the D block of the periodic table? For example, iron, I've got Ar4s2 3d6. I've already done the orbital diagram with it. If this orbital diagram is where you were starting from, and you knew that iron, because it's a metal, loses electrons and becomes a positive ion, which electrons are we going to pull off first? Are we going to be pulling off the 3d electrons, or are we going to be pulling off the 4s electrons? Take a guess. Here's some data to actually back that up a little bit. What I'm really wanting to point out is that this bottom portion of the graph is describing the distance that the electrons are from the nucleus. And you'll notice that just like we were talking about the nodes before, here is where the electron in the 4s orbital is going to show up from time to time, is each one of those spots. You'll also notice that the 3d orbital ends up being closer to the nucleus than the 4s orbital ever gets. Which means if the 4s orbital is further away from the nucleus, which we knew already because it was the 4 number, that means it's a 4th energy level farther away, those are the ones that are going to be removed first. So the electrons further away from the nucleus are always going to be removed first if you're turning it into a positive ion or cation. So if you're looking at the different types of ions of iron, what you'd end up with is Fe2+, where you actually lose both of the 4s electrons, and the Fe+3, which you would not only lose the 2 electrons in the 4s orbital, you also lose that other electron that was doubled up in in that first d orbital. So take a moment, see if you can figure this portion out. Why can tin have either a +2 or a +4 charge? I might be using this as a style of a test question, so you might want to pay particular attention to this one. Give it a try. So if we take a look, I not only wrote out the abbreviated electron configuration for all 3, atom as well as 2 ions, but I also did the orbital diagram for each one of them. So you'll notice that with the tin, I have the 5s2, 4d10, 5p2. And if we are going to start removing 2 electrons, the first 2 that are going to get pulled off are going to be the 5p. While 5p and 5s are both in the same energy level, remember these are going to be the higher energy, and those are going to get pulled off first. Then with the positive 4 charge, all of the 5th period or the 5th energy level electrons got removed. So you'll notice that I have an electron configuration for tin with positive 4 at just 4d10. All right, in summary, photoelectron spectroscopy was used to determine levels and sublevels of electrons. And based with Coulomb's law, a model was developed. And just like you know with Coulomb's law, we've discussed it many times, we got further away from the nucleus, lower attraction, but because we're further away from the nucleus, there's more volume, so you can stick more electrons into it. This also was used to explain the atomic spectral lines. In other words, if you had an electron that was in an excited state and it fell down into a ground state, it would release energy in that process, and that's where those light equations and calculations come in. The model that we determined for sp, d, and f orbitals was actually used to shape the periodic table. So instead of trying to memorize the exact sequence, use a periodic table to figure out what the electron configurations are going to be. With electron configurations in the periodic table, you can predict many different properties as well as explain why they work that way. So some of the ones that you should be able to explain are going to be atomic radius, which we discussed in these notes, ionic radius, which we discussed in these notes. But we didn't explain electronegativity and electron affinity, but you should be able to do that now that we've had this discussion. That's going to summarize what we have for atomic structure. I'm sure there's going to be questions for follow-up later, but this should give you at least a good foundation to be able to do the notes for Chapter 7 and Chapter 8 out of our textbook.